All right, let's talk about significance test for the difference of two means. But before we can get to the tests, we have to talk about the shape, center, and spread of the sampling distribution of x bar 1 minus x bar 2 and conditions that will need to be met. The sampling distribution of x bar 1 minus x bar 2 has the shape, center, spread, as you can see there. This is also in the yellow box on page 631. And if you would like to see a picture of the sampling distribution of the difference of these two sample means, you can look at the bottom of page 629 in your textbook. So these should look very familiar to you because they were similar to what we did in the last couple chapters. The shape, if the population distribution has a shape that's normal, then so will the sampling distribution. Or if we don't know the shape of the population distribution, if we have large enough sample sizes, then the sampling distribution will be shaped normal. Remember the central limit theorem? All right, so the center is unbiased, so it's going to be mu1 minus mu2. And the spread is going to be sigma squared of the first, remember that's your variance, of the first sample divided by the sample size plus the variance of the second sample divided by the sample size. Now remember, you can only use this formula if the 10% condition has been met. And just like with proportions, the standard error of x bar 1 minus x bar 2 is a estimated standard deviation using the sample statistics instead of the parameters. Is this on your formula sheet? Well, let's look. Okay, that was proportions. Here comes means. Yep, there it is. Right here. Okay, so the formula for the standard error is the square root of s squared for the first sample. Remember, that's your variance. S squared for the second sample. And how you interpret this value is this is going to be okay, sorry about that. There was something distracted me out my window. The interpretation of this is basically this is the standard deviation that we're going to use for our sample size. All right, what is the formula for the two sample t statistic? So remember, we're using t because it is means, and we have to use t for means. So the formula for the test statistic, if you'll remember, is always given to you in words. So I'm going to translate these words into symbols. So the test statistic for means is t. And this is going to equal the statistic. So it's going to be x bar 1 minus x bar 2 minus the parameter, which is going to be 0. So if you'll remember, your null hypothesis is going to be x bar 1 equals x bar 2. Not bar. I did that totally wrong because we write our hypotheses based on the parameters, not the sample. See, look, I even make mistakes on occasion. Mu1 equals mu2, which remember we can write as mu1 minus mu2 equals 0. So statistic minus parameter over the standard deviation of the statistic. So of course that's going to be that standard error up there. Remember, standard deviations, we always add variances. So that's why this has a plus in the middle. Okay, so that is our test statistic, and it measures the number of standard deviations away from the mean in a t distribution. All right, so what distribution does the two sample t test statistic have? So it's the t distribution. And we use the t test statistic rather than the z statistic because we do not know the population standard deviation. And how do you calculate degrees of freedom? So if you have your book and want to turn to page 637, at the very bottom of page 637 is the gross and messy formula for finding the degrees of freedom. You will not be provided this formula because it's just gross. So we're going to have two choices for how to calculate your degrees of freedom. We are going to either subtract one from both sample sizes, or we are going to use technology, and I will be sure to show you how to do both, because t-test statistic has to have a degrees of freedom, because as your degrees of freedom increase, the shape of your t-statistic approaches normal. All right, so then the conditions for conducting a two-sample test for mu1 minus mu2. We're going to use this test when the data is random. So, of course, I think these are quite familiar. I'm not going to read them all to you. Just want to point out a couple things. There is this word or here. So there is a choice depending on how the two samples were created. If we have two populations and from which we're drawing a sample, we have to check the first part, that the data comes from simple random samples of both populations. But if we've set up an experiment, we have to make sure that the random assignment was made of the treatment and the control. Again, normal if both of the population distributions are normal, because that would have to be stated for you. You're not going to know that. And if nothing is stated about the shape of the population distribution, then you have to check that central limit theorem. Also remember that you can still use your T procedures if if your sample size is less than 30. Remember how the T procedures are very robust. So we would have to check the graph of the data. So if N is less than 30, you would have to check it for both populations. You check the graph and look for extreme skewness and outliers. All right, let's do a problem. In commercials for Bounty paper towels, the manufacturer claims that they are the quicker picker-upper, but are they also the stronger picker-upper? Two AP Stats students, Wesley and Maverick, decided to find out. They selected a random sample of 30 Bounty paper towels and a random sample of 30 generic paper towels and measured their strength when wet. To do this, they uniformly soaked each paper towel with 4 ounces of water, held two opposite edges of the paper towel, and counted how many quarters each paper towel could hold until it ripped, alternating brands. The box plots to the right display their experiment. Based only on the box plots, think about whether or not you think the mean for Bounty is significantly higher than the mean for generic. Well, hopefully you thought and said, well, that's pretty obvious. Since the centers of the graphs are so far apart, remember we are looking at the average strength, so we're looking at the middle of these pictures. And there is hardly any overlap at all among the two graphs. I mean, if you look at the low end of Bounty, that is just barely one of the high outliers for the generic type of paper towels. So the Bounty mean is way higher. So I would say, based on this alone, we have reason to believe that, yes, Bounty is stronger than the generic brand. Because if the true means were really equal, then you should see these two graphs be closer together with a good amount of overlap, and we don't. So based on our sample, and y'all, that is the heart of this stuff, is something out there appears to be different, or we want to test something that we believe is true. So we take a sample, and this sample result, it looks like we have a significant reason to believe that the Bounty paper towels are stronger than the generic. But to make it statistically significant, we need to run a test, and we need to look at the probability of this outcome actually occurring if there really was no difference between the two strengths for the paper towels. So we're going to run our fun, lovely significance test now. So went ahead and calculated the means and the standard deviations of the samples. Is there convincing evidence that wet Bounty paper towels can hold more weight on average than wet generic paper towels? All right, state. We have to define our parameters. So I'm going to use mu sub b to be the true mean, number of quarters Bounty holds. And I'm going to let mu sub g be the true mean number of quarters the generic brand holds. Our null hypothesis is going to be that the means are the same, or we could write the mu of the Bounty minus the mu of the G is equal to 0, that there is no difference. Remember, we always assume there is no difference. The alternative is that the mean of the Bounty, so the mean number of quarters, is greater than the mean number of quarters the generic holds. So if we write that using the difference, because we're really doing these tests based on the difference, but these are just two different ways to write it. All right, so it will be here, and we want to let alpha equals 0.05. Let's check our conditions. Random sample from both populations is used. Check. Normal. So we did 30 paper towels of each. So both sample sizes are at least 30. Check. Now remember, with independence, we need to check two things. Are the samples independent of each other? Yes. Samples are independent of each other. And remember, we have to check that the individual observations are independent of each other. So technically we sampled without replacement, so we have to check, because once we picked out a paper towel, we didn't put it back in. So we're going to put that, we have to check our 10% condition. And I'm going to say it's safe to assume there's at least 300 paper towels of each brand. Where'd 300 come from? $10 times 30. Y'all, there's 300 paper towels in my cabinet right now. So let's assume that would be a pretty safe assumption to make. So the independent condition has been checked. And also, to kind of throw back to something we did in chapter 9, in the event that you are given a question where the conditions have not been satisfied, you will still proceed and you will make some kind of random comment, not random, you make some kind of comment about, all right, this condition has been, it cannot be satisfied, but we are going to proceed with caution. And then when you write your conclusion, make a comment about how these results may or may not be trustworthy since this condition was not met. But if, all things were perfect, you would write the conclusion based on your p-value. Okay, so state done, plan done, do. Okay, so we're going to do this by hand, and then I'm going to check it in my calculator. So in your do step, we do our test statistic, which is T. and it's going to equal your parameter. I'm sorry, your statistic. So that's going to be, and remember we're doing B minus G, so it's going to be 117.6 minus 88.1 minus your parameter, 0. Remember that comes from your null hypothesis. And then we're going to do the square root of 6.64 squared over 30 plus 6.3 squared over 30. If you want to press pause, type that in your calculator and see if you get a test statistic of about 17.7. I don't even need to touch anything else. Draw your picture. 17.7 is somewhere way down here. So the probability that T is going to be greater than 17.7 is pretty much 0. I'm not even going to type it in the calculator and find out because we know that 17 standard deviations above the mean. That is incredible. That is very statistically significant. All right, so our degrees of freedom. Hang on. I'll be right back. Okay, so our degrees of freedom. Sorry, y'all. I don't know what's happening around here today. Our two sample sizes were 30. So 30 minus 1 is 29. If your two sample sizes had different sizes, so like if one was 30 and one was 33, you would use the smaller of the degrees of freedom sample size minus 1. Now, this is a conservative estimate. Your technology is going to give you a way better estimate. Remember that ugly formula? That's what the technology is going to do. So if we're using technology, so I'm going to switch colors, and we're going to look at the calculator. So if you're going to do the do step in your calculator, remember you have to write down a 2-sample t-test for means. I mean, I would get in the habit of writing that down whether you do the do step by hand or you do the do step in the calculator. It's just mandatory to have it if you are using the calculator. You also need to list your test statistic, T, your p-value, and your degrees of freedom, which I'm going to show you how to get from your calculator. All right, so you go to your calculator, stat, over to tests. We're doing a 2-sample t-test. Real quick side note, a 2-sample z-test would be if we knew the population's standard deviation. You're never going to know that. Like, I don't even understand why this test exists, like number 3 here, because if you know the population's standard deviation, then you know the population's mean because you have to use the mean to find the standard deviation. And if you know the means, the true means, can't we just use them? We wouldn't need to run a test. So again, I don't know why number 3 is here, but be very careful that you don't choose it. You are always going to be doing a t-test for means. Okay, so number 4. Now we have a choice. We can input the data or we can use the statistics. And so this problem gave you the statistics. So we're going to put those in. So X bar 1 was 117.6. The standard deviation for the first sample was 6.64. The sample size was 30. Your second mean was 88.1. Standard deviation is 6.3 and 30. And we thought we were pretty daggone sure that the first mean is greater than the second mean. So we've already had that select. Now, when you are entering your stuff in your calculator for a 2-sample t-test, you are not going to pool. So let's reflect. You only pool for proportions. Easy to remember, PP. You only pool for proportions. All right, so calculate. So our degrees of freedom are 16.65. I said the wrong thing. T-value 16.65, which I got 17.7. Oh, wait. Hold the phone. That's 17.65, not 16.65. Your p-value is 2.9 times 10 to the negative 25, which is basically 0. And you can see your degrees of freedom is 57.8. And we used a degree of freedom of 29. So please remember that you've got two choices for degrees of freedom for your t-test. The calculator gives you the accurate degrees of freedom, but you can use a conservative degrees of freedom by subtracting 1 from both your sample sizes and picking the smallest number. All right, so let's interpret this p-value in context. All right, so since the p-value is basically 0, it is almost impossible. And hopefully, if you know anything from this class, is nothing is really impossible, but this is as close to impossible as we can statistically get. It is almost impossible to get a difference in the mean number of quarters of 29.5, and I hope you know 29.5 came from subtracting the two sample means and actually finding the difference, of 29.5 quarters by chance alone. If there really was no difference in the mean number of quarters, the towels would hold. And that's significance tests for